Hello and welcome to the video on 7.4, which is a one sample interval, which these are probably the most important because they're probably used the most in real life because this is the assumption that the standard deviation is unknown. So here's the setup for this. I have some population. I'm interested in capturing this mu. So along with this mu comes this standard deviation, which is standard deviation of everybody in your population. So when we reach in the interior and take this sample, okay, which is a portion of these people, I'm going to go ahead and get an x bar. But along with an x bar, I'm going to get the standard deviation. How much variance do I have, or how much variability do I have within each x in the one sample? So, for example, let's say I take 50 people. That's going to give me 50 different x's. Okay, that's going to give me 50 different of these x's. S would be the variability of these 50 people. Okay, so S would be the variability of these 50 people. Okay, so what happens here is this is unknown, which in real life it's probably going to be unknown because we're not going to know either of these guys because they're from these populations, and usually these populations have many objects or items or people or subjects, or there's a lot in our population. That's why we're taking a sample in the first place. Okay, so it's not we generally don't know either of these values. Okay, so with the last chapter, this was known. Okay, this guy was known, and we used z's for our critical values. Okay, and these just you could find on your chart. Um, okay, or you could use or you could find them in statcrunch. If this is unknown, we have to go from the z to a t distribution. Okay, and the t distribution is a lot more complicated than the z because there's only one z distribution. Okay, so the t is different because basically there is a t distribution for every sample size. Okay, and what determines our z distribution is this thing called the degree of freedom. So the degree of freedom, let me write that out. The degree of freedom is always equal to, we always call that df, it's always equal to your sample size minus 1. So it's not that complicated, but you just have to know it because for every degree of freedom there's a t distribution. So the critical values are going to change for every single different distribution. Now when you start getting into sample sizes, um, say in the hundreds and thousands, then the t distributions will look like the z's. But for example, if I took 10 people, then my degree of freedom would be equal to 9. So when you find your confidence interval, okay, we're not in z's anymore, we're in t's. Okay, so what's going to happen is there's a lot more variability in t's than z's. Okay, so your critical values are going to change. So if you remember, okay, if you remember the concept of sampling variability and all these things, okay, so what happens is you get all these. If I go in and take a sample, you're in this distribution with all these sample means. Now if you remember, the average of all your x bars is equal to mu. That's not going to change. The standard deviation, if you remember, was the original standard deviation over the square root of n. But there's a problem here in that I don't know what. You don't know this original standard deviation, so the next best thing we could do is use s. You see how x bar estimates that? So we could use s to estimate sigma. So this is just going to be an s now. Okay? So this is how much these x bars will vary. And that's why we use a t distribution. Okay? So the t distribution is the same thing as the is the z distribution. So the t-score, I don't know if, let's just do a little quick review. The z distribution, remember, was x minus mu over the standard deviation. So let me give you another one. You could change these z's, x minus, okay? So this is when I'm dealing with x bars. So this is the population, this is the sampling distribution. Well, t is basically the same thing, but it's just x bar minus mu over s over the square root of n. It's just how many standard deviations away. It always depends on your n, whichever one that we enter. See, n didn't matter, okay? And here the central limit comes into effect too. Okay, so the central limit theorem says that if n is basically around 30, depending on what the original distribution looks like, okay, then the sampling distribution is approximately normal. Okay, so let me talk about this for a second because there's some homework problems on it. So let's say this was my population distribution. Okay, that's my population distribution. So this is skewed right, pretty bad. So what happens here is, let's say my n was equal to 10. If I was n is equal to 10 and I graphed all x bars, then it's not guaranteed to be normal, because the central limit theorem says what? Has to be 30. Okay, but if they tell me the population is normal, so that's normal, okay, with standard deviation, then n doesn't matter, then the size doesn't matter, the sample size doesn't matter, because it doesn't matter what you take. If you take 2, if you take 3 out of there, if you take 4, and so on, okay, the graph of all your x bars will be normal. Okay, so that's in the homework, which we'll kind of go over. So let's go to the next page and let's talk about this confidence interval. So it's the same formula. Now if this is known, if the standard deviation of population is known, if you remember, it was x plus or minus z star times this over the square root of, can't do a square root today, over the square root of n. Okay, but what if this is unknown? Let's talk about the difference, because it's basically the same, almost the same thing. So if this is unknown, then you're still going to get an x bar plus or minus, but this is unknown, so we have to use what's called a t star. So you have to learn how to find t star. All over s over the square root of n. Okay, so everything's the same pretty much. And then for this case, okay, we have a condition. We have a couple of conditions. If the population distribution, if the original distribution is not approximately normal, then n has to be greater than or equal to 30, around 30. Okay? If it is, then we're free to go. And sometimes I'll use this alpha divided by 2. This is just a one-tailed area. Okay? So for example, if they wanted a 90% confidence interval, okay, the alpha is 1 minus this guy. So if they want, all they're saying there is that this is going to be 5%. That's what this means, okay? Because alpha equals 1 minus 0.9. That gives me the outsides. See, that gives me this and this. Okay? So if alpha, if the confidence interval is 90%, alpha would equal 10%. Okay? But I don't want that. I want the one-tailed probability. This is two tails. I only want one tail. So if it's 10%, I just divide that by 2, which is going to give me 5%, 0.05. Okay? So I'm gonna teach you how to do this. This depends on the degree of freedom. Okay? Sometimes they'll do this. That means that the sample size was 9. Okay, this is like an upper statistics classes. This one I don't think it does it, but it kind of tells you what to do. Okay, so now let's go and do some of the homeworks and show you that it's really not all that bad. Okay. And if you're interested in going on, we want to play with this formula a little bit, okay? Okay, so let's do this. 10% n equals 5, so the degree of freedom, if n equals 5, the degree of freedom will be 4. Okay? So now let's do some of these, okay? So do one of the following appropriate. Find the value of z, find the critical value of t, state that neither the normal nor the t applies. Confidence level of 90%, n equals 27. This is unknown. See, the population appears to be normally distributed, so that means n doesn't matter. Okay? So you see this is unknown. Would we use a z or a t? When this is unknown, we always use a t. So it's either going to be b or c. Since this is normally distributed, this n could be less than 30 and I'm still good. Okay, so this is how you do this. You have to go to statcrunch. Okay, you have to go to statcrunch. Let me show you on a picture real quick. So I want a 90%. I want a 90%. Oh, why'd that go away? Now remember, we're in t's now. Okay, so this is 0, and I'm looking for 90% to the left. Now tf divided by 2 means that what's the shaded region? What's this? If the middle is 90, what is this region right here? That would be 5%. Correct? If the middle is 90, then this is 5, or this is 5. So when I go to my t, go to my t, see there's my t. If you remember, we took 27. Let's see where this went. I have to put it in here, so push that out of the way. It's better just to make this a lot smaller. See right here, we took 27, so my degree of freedom is 26. Okay, so to find my z-star, all I need to do is find this right. This right needs to be 5%. See, this needs to be 0.05. It's going to switch it on me for some reason. It does that sometimes. Nope. See? 0.05, that's to the right. Degree of freedom 26, that's 27. 1.706 right there. Check answer. That's it. Okay, let's do another one. Okay, do one of the following. Find the z, find the critical value t, state whether neither normal. Okay, so 90%, n is equal to 15. This is known. Population appears to be very skewed. If the population is very skewed and I don't have 15, then the graph of my x bars will not be normal. Stay with it. Okay. You see this 15 right here? This being known will not make my sampling distribution of all my x bars normal. Okay, so this does apply for z's and t's. Doesn't matter. Just because I know this isn't going to give me normality. Since it's very skewed, you need more people. I might need 40 here or 50. Okay, so neither normal nor t applies here. Okay, I hope you guys understand that you have to use the central limit theorem. Okay, have to use the central limit theorem. Okay, so this is another one. Okay, so see, since I know this, okay, since I know this might, so I'm going to use a z, so it's either b or d. The population appears to be skewed, but it doesn't matter because you have 200 people. 200 is plenty bigger than 30 to make my sampling distribution relatively normal. So this is going to be 1.645 just because I know it, but I'm going to show you how to do it. So go stat calculator. In this case, we're in the normal distribution. Okay, I like having that thing available. So if you want this, if 90% is in the middle, what's here on the right? 5%. Okay, and I want this to be greater than. And just make sure I'm okay here. 0.05. That should be right. That should be right. Okay, I had 2 decimals there. So 0.0. See if 90 is in the middle, then 5% is to the right. 1.645. Okay, so I just proved it to you. That's how you find your critical values. Okay, so let's go to a confidence interval, 99 confidence interval. Okay, so if you look here, I have this many babies, so n's that. Okay, the mean of this and the standard deviation is this. Now the standard deviation is actually from my sample and not the population. This was the standard deviation of these 186 babies. So we want to go stat, go to my t statistic, one sample. Okay, I don't have data. So the sample mean, these problems they're pretty basic. 3103. Sample standard deviation is 687, and the sample size I took 186. Okay, we want to do a confidence interval of 0.99, and let's go ahead and calculate this. And this is my lower. What do I want to round to? Nearest integer. Round to the nearest integer. So let's go to 2972. And let's go to 3234. Yep, and that's it. Okay. What is the best estimate? Okay, data set includes 109 body temperatures of healthy adults for which the X bar was 90. Okay, the best point estimate, remember the point estimate is just the average, that's all I have. The best thing I have to estimate the real thing is the average. Okay. Okay, so 99% confidence interval. So use this, okay, to create an interval. So all you have to do is stat t one sample summary. Okay, put the data in there. Now it says 98.6. Okay, if 98.6 falls in the interval, that means that's not out of the ordinary. Okay, so you guys should be able to do that. Same thing. Okay, all you have to do is put the data in there. Okay, so this problem you have to open in statcrunch instead of saying, okay, so we want to open this in statcrunch. So now this is not a summary, this is actually a data problem. Okay, so I'll just get you started here. So you have your data in here. So when we go to our t statistic, we're going to say with data. Hey, there you go. Next, we want a confidence interval. See, these are actually easy. Change that to 99, 95%. Calculate. So the mean, okay, this is your lower and that's your upper. Okay, whatever that question is about. Here's another one. Do this the same way. Open this up. There's no backwards problems on these, so that's the good thing to know. Now, if you want, get practice and play with these things. Put them in these formulas if you have extra time, and your understanding of this stuff will go way up. Okay, so that's it for 7.4, and good luck.